In our previous sessions, we have looked at Taylor's theorem or Taylor's series. Remember, let f of x, which can be expanded in powers of h, and the expansion be differentiable any number of times. Then f of x plus h is equal to this. Yes, so we have looked at Taylor's theorem and Maclaurin's theorem, and we saw how to expand or how to generate the expansion of log of sine of x. Now what we are going to do is we are going to look at a function of two variables, that is x and y. Okay, so if the function of two variables and all its partial derivatives up to nth order are finite and continuous for all points of x and y, and x is between a and a plus h and y is between b and b plus k, then f of a plus h comma b plus k would be equal to f of a comma b plus h of f x plus k f y. Now here this x stands for x and y. It stands for the first partial derivative. In this case it is first partial derivative with respect to x. Here it is first partial derivative with respect to y, plus 2 factorial times h square f of x. Now here it means this is the second partial derivative of f with respect to x, plus 2hk f xy. Here it is partial derivative of f with respect to x and y. So k square f yy, that is partial derivative, second partial derivative with respect to y, and we can keep going like this, 1 by 3 factorial, and we will have h cube by 3 factorial. The 3 factorial I have already written, h cube f x x x, that is the third partial derivative with respect to, plus 3h square k f of x xy plus 3h cube, no, h times k square f xyy plus k cube f yyyy. Now here this looks very complicated, right? But think of it like this. Here just focus on the h and k. So let's focus on h first. So you will notice that here it is 1, right? H to the power of 1 is there. Here h to the power of 2 is there. Here it is 1 is there, 2 is there. Oh, sorry, 0, because it is not there. Yes, 3, 2, 1 and 0. So here h, exponent of h is reducing and k is increasing. And what about the coefficients? Here we have 2, here there is nothing, so it is 1, 2, 1. Here it is 1, 3, 3, 1. Yes. So here the coefficients are 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Remember this Pascal's triangle, right? So we can write it in terms of combinations as well. Okay, now here all the partial derivatives are at a comma b. Now if a plus h is equal to x and b plus k is equal to y, then x becomes equal to, no, h becomes equal to x minus a and k becomes equal to y minus b. So what will happen here now? It will become f of x comma y is equal to f of a comma b. Here what was it? F of a comma b plus x minus a. What we are doing is substituting in place of h x minus a, in place of k y minus b. So x minus a f x a b plus y minus b f y of a comma b plus x minus a. Remember this is h, this is h, x minus a we are substituting in place of h. So x minus a square by 2 factorial f of x x a comma b plus 2 times x minus a y minus b by 2 factorial f of xy f xy of a comma b, and we can take it to the next term as well. So x minus a cube by 3 factorial f x x x of a comma b plus 2 x minus, no, not 2, 3 x minus a square y minus b by 3 factorial f x x y of a comma b plus 3 times x minus a cube, no, not cube, x minus a y minus b square. You have to be very careful while writing this. F x y y of a comma b, and finally plus times x minus a will disappear, y minus b cube by 3 factorial f y y y of a comma b. So this is separate and this is right. Looks very complicated. Just study it. If you remember this, just by doing the substitution in place of h and k, you will get this, and so on. Now if we make a is equal to 0 and b equal to 0 in the above, what will happen? What we'll get is the Maclaurin's form of the Taylor series or Taylor's theorem. So let's put that. We will get f of x comma y is equal to f of 0 comma 0 plus x f x 0 comma 0, because this is x minus a, so a is 0, so x is left, plus y, again y minus b, b is 0, so f of y, f of fy of 0 comma 0, plus then what do we have? We have x minus a square, a is 0, so x square by 2 factorial f x x of 0 comma 0 plus 2xy by 2 factorial f xy of 0 comma 0 plus y square by 2 factorial f of f yy of 0 comma 0 plus x cube by 3 factorial f x x x of 0 comma 0 plus 3x square y by 3 factorial f x x y plus 3xy square by 3 factorial f x y y of 0 comma 0. This is 0 comma 0, and finally no 3 this time, y cube by 3 factorial f y y y of 0 comma 0, and so on. Now this is 1, this is second, this is third, this is fourth. Okay, now this is the Maclaurin's form of the Taylor's theorem. Here remember, in which order you do the partial differentiation doesn't matter. You have to remember this. So dou square f by dou x dou y is equal to dou square f by dou y dou x. So this order of differentiation doesn't matter. Okay, so let's actually solve a problem and see how it works out. So let's say we have to expand e to the power of x sine y. So previously, if you have noticed in our previous session on Taylor's theorem, we would not have found x and y. We would have got it as f of x is equal to sine x, or an expression with a single variable. Now we have two variables. Okay, so let's start off. How will we proceed? What we'll do is, first we'll write the f of xy itself. So that is e to the power of x sine y. Now systematically we will start partially differentiating it. F x x comma y. So we are going to differentiate f of xy with respect to x partially. So e to the power of x, its differentiation is e to the power of x itself. Sine y remains as it is. Then we are going to differentiate, partially differentiate with respect to y. Now here what happens, e to the power of x is treated as a constant, and we differentiate sine y. So that is cos y. Okay, f x x of x comma y. So here we will take this and differentiate it again with respect to x. So it is still e to the power of x sine y. Now we will differentiate partially with respect to x and y. So we can take x or y. So if we take this, we differentiate this with respect to y. If we take this, we differentiate this with respect to x. So you can take any one. So this comes to e to the power of x cos y. Okay, then f y y, x comma y. Now what we'll do is, we'll take this, because it's already partially differentiated with respect to y, and partially differentiated again by y. So e to the power of x. Now cos y is what? Cos differential of cos y is minus sine y. Okay, f x of x comma y. So take xx and differentiate it again by x. So e to the power of x sine y, differentiating it with respect to x gives us the same thing. So e to the power of x sine y. Now xy. Now let's take xx and differentiate it with respect to y. So e to the power of x cos y. So we took this and differentiated it with respect to y partially. Now f xy of x comma y. This gives us, so here what we'll do is we'll take xy and differentiate it with respect to y again. So we get e to the power of x cos y is minus sine y. So minus sine y. And finally f of y x comma y equal to, now we'll take y and differentiate it again with respect to y partially. So here we have e to the power of minus e to the power of x sine y. So this becomes minus e to the power of x sine y is nothing but cos y. Now if you want to proceed further, again follow the same procedure. Okay, now one thing that I didn't mention here is that we have to write it in terms of powers of x and y. Okay, and we'll stop at the third degree. Now since we have not been told at which point, we assume it is 0 comma 0. So f of 0 comma 0 would be e to the power of 0 is 1, sine 0 is 0. So 1 times 0 equal to 0. Again f x 0 comma 0 is equal to e to the power of x is 1, sine 0 is 0. So 0. f y 0 comma 0 is equal to, now e to the power of 0 is 1, cos 0 is 1. So this is equal to 1. f x at 0 comma 0 is equal to e to the power of x is 1, e to the power of 0 is 1, sine 0 is 0. So this is 0. So you might have noticed by now that wherever it is sine, it is 0. Wherever it is cos, it is going to be 1. So 0 comma 0 is equal to, cos is there, so 1 times 1 equal to f y 0 0 is equal to minus 1 times 0, which is 0. f x 0 comma 0 is equal to 1 times 0 equal to 0. x y at 0 comma 0 is equal to 1 times 1 equal to 0. 1 times 1 is equal to 1. f x y 0 comma 0 is equal to minus 1 times 0, which is 0. y at 0 comma 0 is equal to minus 1 times 1 minus 1. So many of our terms have actually disappeared because of this. But let's actually put it and see. What I would suggest is, till you become comfortable, you write this, the standard form. F of 0 comma 0 plus x f x 0 comma 0 plus y f y 0 comma 0 plus then x square by 2 factorial f of fxx of 0 comma 0 plus 2xy by 2 factorial fxy 0 comma 0 plus y square by 2 factorial fyy 0 comma 0 plus x cube by 3 factorial fxxx 0 comma 0. Till you get comfortable, you write the standard form and then apply it in a given context. 3x square y by 3 factorial xxy 0 comma 0 plus 3xy square by 3 factorial fxyy 0 comma 0 plus y cube by 3 factorial fyy of 0 0 and so on. Now we can do the substitutions. Yes, so f of 0 comma 0 would be 0. Here if you notice, it is 0. The second is also 0. So plus x times 0 plus y times the next term is 1 plus x square by 2 factorial 0 plus 2xy by 2 factorial times 1. So here 2 and 2 gets cancelled plus y square by 2 factorial times 0 plus x cube by 3 factorial times 0 plus x square y by 3 factorial times 1 plus xy square by 3 factorial times 0 and finally y cube by 3 factorial times minus 1 and so on. Okay, so here we can ignore this 0 0 0. This is y, this is 0, this is again 1, so plus xy plus this is 0, this is 0. Here it is x square y by 3 factorial. This should have been 3. This should have been 3. So here 3 factorial and 3 gets cancelled and you are left with 2. So this will be plus 0 and here it will become minus y cube by 6 and so on. Okay, so this is the Maclaurin series or a special case of Taylor's series. Okay, shall we do one more quickly? Let's say x square y plus 3y minus 2. Now we have to expand this in powers of x minus 1 and y plus 2. Okay, so now here we can say h is equal to x minus 1 and k is equal to y plus 2, because that is what the powers goes in as standard form of f of x comma y. F of x comma y is equal to x square y plus 3y minus 2. So here a plus h is equal to x. So here a plus h is x minus 1. So x and x gets cancelled and a is equal to 1. Similarly, b plus k is equal to y. K is y plus 2 equal to y. So y gets cancelled and b is equal to minus 2. So that means we are looking at f of 1 comma minus 2. This is what we are looking at. So let's start off. F of x comma y as it is, x square y plus 3y minus 2. Now we'll start differentiation. So with respect to x, partially gives us 2xy. These two become constants. Fy of x comma y. So partially differentiating with respect to y, we get x square plus 3. Now again partially differentiating with respect to x twice. What we can do for that is take this itself, we have already differentiated with partially with respect to x, and differentiate it again partially with respect to x. So we get 2y. Okay, now fxy. For this we can take fx, or we can take fy. Remember, the order of differentiation doesn't matter. So if we take this, we differentiate with respect to y, we get 2x. Yes. Whereas if we take this, again we get 2x. Yes. In this case, if we take this, we differentiate it with respect to x. So in either case, we will get 2x. Okay. Now y. Now in this case, we take this and differentiate it again with respect to y. So here it is 0. X comma y is equal to, now we take this and differentiate it again with respect to x. So this is going to be 0. Xy. So we already have xy. Let's differentiate it again with respect to x. So we get 2. Fxyy. So xyy, we already have yy. Differentiate with respect to x, 0. Yy. Now here yy we already have. So doing it again, we get 0. Okay. So now that we have this in place, now we just evaluate them at this point, 1 comma minus 2. So 1 square minus 2 plus 3 times minus 2 minus 2 minus 2 minus 6 minus 2, which is minus 10. This is 2 times 1 time minus 2, which is minus 4. This is x square, that is 1 plus 3 equal to 4. This is 2 times minus 2 equal to minus 4. 2 times 1, which is 2, and this is 0, and here again it will be 0. This is 2, and these will be 0. Okay. Now what do? We apply these values or substitute these values in our x square y plus 3y minus 2 is equal to f of 1 comma minus 2 plus x f of x 1 minus 2 plus y f y 1 comma minus 2 plus, again I'm just writing it the standard form itself first of all by just putting the values of x and y, and then we will see evaluating those. So it now will be x square by 2 factorial fxx 1 comma minus 2 plus 2xy by 2 factorial fxy 1 comma minus 2 plus y square by 2 factorial yy of 1 comma minus 2 plus x cube by 3 factorial fxxx 1 comma minus 2 plus 3x square by 3 factorial 3x square y fxxy 1 comma minus 2 plus 3xy square by 3 factorial fxyy, and finally y cube by 3 factorial fyyyy 1 comma minus 2, and so on. Now let's substitute the values. Minus 10 plus, here we don't have x, we have x minus 1 minus 4. So this is the x part and this is the f of fx, plus y plus 2, this is the y part, and this is the fy part, plus x minus 1 square by 2 factorial minus 4 plus 2 times x minus 1 y plus 2 by 2 factorial times 2 plus y plus 2 square by 2 factorial times 0 plus x minus 1 cube. Remember, this is together and this is together, so that you can see that the exponent of this keeps decreasing, and here again we start afresh. So you could look at it as a plus b the whole square and this as a plus b the whole cube. So x minus 1 cube by 3 factorial times 0 plus 3x minus 1 square y plus 2 by 3 factorial times 2 plus 3 times x minus 1 y plus 2 square by 3 factorial times 0 plus y plus 2 the whole cube by 3 factorial times 0, and so on. Now here if you look at it, this goes off because of this 0, this goes off, this goes off, this goes off, okay, and what we are left with is minus 10 minus 4x minus 1 plus 4y plus 2 minus 4x minus 1 square by 2, so this becomes 2 plus 4x minus 1 y plus 2 by 2 factorial, so 2 plus 0 plus 0 plus x minus 1 square y plus 2 by 3 factorial, and this is times, what have I put here, x minus 1 square, this is 3 times 2. So here 3 factorial is 3 times 2, so this 3 and this 3 cancels, this 2 and this 2 cancels, plus 0 plus 0. So this is equal to 10 minus 4 times x minus 1 minus 10 plus 4 times y plus 2 minus 2 times x minus 1 square plus 2 times x minus 1 y plus 2 plus x minus 1 square y plus 2, and so on, and this is x square y plus 3y minus 2. Yes, so this is Taylor's theorem in 2 variables. Practice. Bye for now.